In this video, we're going to talk about enthalpy changes. And specifically, we're going to talk about the enthalpy change of formation and how that relates to Hess's law. Now, the enthalpy change of formation is the enthalpy change when 1 mole of a product is formed from its constituent elements under standard conditions. But what does that mean? It's better off to think of it as an equation. So in this equation, you can see that we have 1 mole of a product. This product at this time is water. So we've got that part of our definition. The next part is the constituent elements. So you can see here, we've got the elements that make up water. The last thing is standard conditions. Now, standard conditions is 298 Kelvin, and it's also 100 kilopascals. And basically, it's round about slightly above room temperature. So you would expect hydrogen to be a gas at that temperature, you would expect oxygen to be a gas, and you would expect water to be a liquid. And they're called the standard states. Now, if we put that to the side and then practice our actual enthalpy change of formation equations. So the first thing is, as a tip, is that use halves, because we're only basing this on 1 mole. So you can just do halves to make sure that, for example, if you're using O2, you put half O2, you'll get 1 oxygen in your product. Next thing is, and this is for your calculations, enthalpy changes of formation of elements are equal or is equal to 0. Now that would be good for your calculations, but for now, we'll just think about the equations themselves. Now the equations that you're going to do, you can do them before I do them. So I'm going to do 2 different examples. So the first example I'm going to do is magnesium and magnesium nitrate. So feel free, write the equation now, stop the video, make it interactive, don't just sit there and watch and see if you can do it. Now the next one we're going to do is C2H5OH, which is ethanol. Now, how do you do this? So what you first look at is, what are they made of? So this is made of magnesium, nitrogen, and oxygen. It's 1 mole, so we work our way back, and we say, right, we're going to have, this is going to be made out of oxygen, and it's going to be made out of nitrogen, and it's going to be made out of magnesium. Now, if that is the case, I need to think of something called Hofbrinkel. So Hofbrinkel is our diatomic elements. So Hofbrin, as in nitrogen, and Hof with the R in the centre is the oxygen. So they are our diatomic elements. And then what we do is we look here and say, well, how many nitrogens are there? Hopefully you can see that there are 2 nitrogens there, so I can keep my N2. And if you look here, there are also 6 oxygens. So that would be plus 3O2. So I've got the right balancing here, but I haven't done my state symbols because it's at standard conditions. So magnesium is a metal, so it's a solid. Nitrogen is normally a gas, okay, and then oxygen is also a gas. Now, you'll be given this in the test, so don't worry about this, but your product, okay, if you don't recognize what it is, you don't know what standard state it is, it will be given if it's something slightly weird, okay, and this one is a solid, so don't worry about that. We then go for the other one here, which is ethanol. Okay, and hopefully you realise ethanol is a liquid because it's in alcoholic drinks, so that's an L. We just go back, we've got carbon, we've got hydrogen, and we've got oxygen. So all we have to do is go carbon, hydrogen, and oxygen. Again, we go back to Hofbrinkel. So Hofbrinkel, H and O, so there are diatomic elements. And hopefully you realise that the hydrogen and the oxygen are gases, and now we just have to do our balancing. So if you look here, there's 1 oxygen, so that'll be half O2. There are 6 hydrogens, so 3 of that, and just to finish off, your carbon is a solid because you just missed that off. And that's balancing wise, 2 carbons there, so 2 carbons here. So what we have now is 2 enthalpy changes of formation where we've made 1 mole of product and 1 mole of product there from its constituent elements at their standard states. So now that we know how to do the equations for enthalpy change of formation, we're going to see how we can apply it using Hess's law. Now this definition is not in green because you don't need to remember it. You need to understand it, but not remember it. Now what it means is it doesn't matter what route you take through a chemical reaction, so you can take two different routes. As long as the initial and final conditions are the same, then each route will have the same enthalpy change. Again, doesn't make much sense like this, so let's do it in picture form. So we have a reaction here, delta RH, as in the R stands for reaction, and this can be any reaction whatsoever. It can be 1, 2, 3 moles, it doesn't really matter, it's just any reaction that's stated. Now, if we then take A, and don't take it to B, we're going to take it to C. And we're going to label that as 1. And then we're going to take C back to B, which means we're going to label that as 2. So notice our initial and final conditions at A go to B, and here our initial and final conditions are still going to be B. So we have two routes that are ending up in the same place. That means our enthalpy change for A to B is going to be the same as our enthalpy change for A through to C to B. But let's look at how we can see that working pictorially again. So we've got delta RH there, and we've got the two reactions, 1 and 2, down there. Now if you think of it like a circle, I know it's a triangle, but we can have loads of different shapes of these things. So if you go like this, you can see that's going anti-clockwise. So that means those two arrows are going anti-clockwise. This arrow is going in a clockwise direction. So they're going in opposite directions. So that means you could add 1 and 2 together and it will equal R. Okay, because if the enthalpy change of this is the same, okay, you've just got to add the two together. If the arrows are going in the same direction, you can add them together. And that ends up in this expression here. So R is equal to 1 plus 2. So let's have a look at this, but in a slightly more complicated fashion. And we're going to swap one of the arrows. So you notice this arrow right here is now pointing downwards. Now, when it's pointing downwards here, we've got 1 and we've got 2, and we still need to look at which arrows are going in the same direction. So hopefully you can see now which ones are going in the same direction. Let's bring our arrow out again, and you can see R and 2 are going in the same direction. They're both going clockwise. And that means the other one's going anti-clockwise. That means this time 1 is going to be equal to R plus 2. Now that means you can just rearrange this so that R is equal to 1 minus 2. Now there's a simpler way of doing it if you're a mathematician, and I'm not, so I quite like this pictorial way. But if you're a mathematician, you can just say this. If I swap this arrow and make it so it points up, this delta 2H becomes minus delta 2H. Okay, because enthalpy changes in one direction. If it's a positive in one direction, it will be the exact same number but negative in the opposite direction. So if I then turn this arrow around and point it upwards, this will just go to minus delta 2H. And if that's the case, and you add these two together, it will be delta 1H minus delta 2H, which is exactly the same thing as you've got there. So we've now moved on to a different example. And again using Hess's law. So we've got these arrows looking like we did on the other one. And don't worry if it's a triangle, a square, or anything like that. You're just simply going to look at the arrows. So if we look at the arrow here, that is going in opposite direction to that arrow. And if you use my circle before, it's going in a more of a clockwise direction. And then you can see all of these are going in the same direction, which is that anti-clockwise direction. So what we can do is we can say delta RH is equal to 1 plus 2 plus 3. So 1 plus 2 plus 3. And as long as you know what those enthalpy changes are within those reactions, you can just add them together. And we'll talk about how you do that next. So before we do our energy cycle, or Hess's cycle, or even enthalpy cycle, all the same thing, we need to remind ourselves of the enthalpy change of formation. Really important, 1 mole of a product made from those constituent elements. And we practiced those earlier in the video, so hopefully you're good with those. Now, the question we've got here is where we take ethane, C2H6, and we combust it to make carbon dioxide and water. And this is our enthalpy change of reaction. Now for this question, what we want you to do is calculate what the enthalpy change of reaction is for this reaction. And we're given the enthalpy changes of formation. Now, how do we know that? We know that because there is an F in the middle of the delta and the H, and it tells us that these are the enthalpy changes of formation values for these compounds. Now, we're going to put our equation out again, okay, and that's our delta RH, as we said. Now at this point, let's put the question over to the side, give ourselves a bit more space, and we can see here that we've got our first arrow coming up. Now let's explain why have we put this arrow here. We put this arrow here because, as you can see highlighted here, C2H6. We're making C2H6 if the arrow goes in this direction. Just ignore this part here and just think about this part here, going from there to there. We're making 1 mole of C2H6 from the constituent elements. Now, the oxygen is not changing, so there's no energy change there. It's just the energy change for the 2 carbons and the 3 hydrogen molecules going here. Often the mistakes people made is they don't put the diatomic elements as diatomic: oxygen, hydrogen, fluorine, chlorine, etc. Now we've highlighted the C2H6 here, and so it says for 1 mole of C2H6 being produced, there'll be an enthalpy change of -85. So delta 1H will be -85. The next part is to highlight the CO2 and the H2O. So the CO2 and the H2O, okay, this time there's 3 and 2. And we've got the enthalpy changes of formation values here. So the arrow needs to go from the constituent elements going up here. And you'll find if you balance this properly, this will balance properly. It's no problem. So the arrow goes up, okay, and you can see constituent elements of carbon dioxide and water. So don't worry about balancing this part really anymore from this point, because the first bit you balance, because no balancing changes in the above equation, if you balance this one, it'll be balanced this way. Okay. Now this is all to get the expression. There's 2 ways of getting the expression, and we'll go through the second way in the next example. But here again, as we did earlier, we've got the rotating wheel here essentially. You can see that the green ones, the green arrows that have been drawn, they're deliberately in that colour, are going in this clockwise direction. You can see that the orange one is going in the anti-clockwise direction. That means we can add R to 1 and it will equal 2. Then we can just rearrange that, so we get 2 minus 1 is equal to our enthalpy change of reaction. And that's all we need to draw the Hess cycle for, to get that. So from this point onwards, we'll put the Hess cycle down and put our expression up here. Now we still need this just to see the balancing really, but it's really the top equation that we need. So we're going to do this in order. So we've got 2 first and then 1. So let's work out what 2 is. That's all you have to do is, once you've worked out the expression, is work out what 2 and 1 equal. So if that's the case, okay, we've got delta 2H. Now delta 2H, if you look at it over here, hopefully you're starting to work it out here. As we go up here, we're making 2 moles of the carbon dioxide. Now, enthalpy change of formation is based on 1 mole. So if I then go over here, and I can see that CO2 is -286, okay, and there are 2 moles of it. So therefore, it would be 2 times -286. Now that is counted for our carbon dioxide, 2 times -286. Then we take that, and in this equation I'm still making water as well. Water is -394. You look in the corner there, -394. So I'll add that to -394, okay, but I'm going to times that 394 by 3, because there are 3 moles of that water being produced. Now, if that's the case, and you put that into a calculator, hopefully you're putting it in now, right? Don't just watch the video, do the calculation. And you put it into your calculator and it'll be a -1754. And that'll be in kilojoules per mole. We then go for delta 1H, which is a bit nicer, because if you look at delta 1H, you're making 1 mole of C2H6. If you go over here, C2H6 at the top says -85. So literally, that is just -85. So we've got our 2 values. We've got 1 and we've got 2. All we have to do is put them into that expression. So if we put it into that expression, that's going to be delta RH is going to be equal. We've got 2 first, so that's minus 1754. Okay, and then it says minus. So it'll be, and the delta 1h is minus 85. So that'll be minus, minus, and then that is 85. Now a minus, minus, hopefully if you've done your maths, is a plus. Okay, so that means plus 85. Which means overall, that will be equal to minus 1669, and that will be kilojoules per mole. Okay, and that's our delta RH. Now the really important thing is when you're doing formation values, you just get formation values. Let's just say you get tables that just have formation values in. Those formation values have to have the arrows pointing upwards because they're forming their products, and their products are the reactants of the delta RH and the products of the delta RH. So I'm making these. So you'll always see the arrows going upwards and outwards like that if you're just given enthalpy change of formation values. And that is how you calculate an enthalpy change of formation energy cycle. We're now going to go on to our second example of energy cycles with the enthalpy change of formation. Now, here again, we've got our definition for the enthalpy change of formation, just to remind you. And we're going to put our question in front of you. You can see synthesis of ammonium chloride. We've got ammonia plus hydrochloric acid going to ammonium chloride. We want you to work out the enthalpy change of this reaction. We're doing it with the enthalpy changes of formation, which are given here. So please, do not wait for me to explain this. Stop the video, do the question, okay? But for those of you who haven't stopped the video and want to watch me, here we go, here's how you do it. So again, we put our equation down at the bottom and then we make ourselves some space. We put our delta RH and then make ourselves some space. There we have, and I've highlighted straight away, we've gone straight into the arrow that's pointing upwards from the constituent elements. So here are the constituent elements of these two reactants. Okay, there's 4 hydrogens there, 4 there, there's one nitrogen, which is half a nitrogen molecule here, and 1 chlorine, which is half a chlorine molecule there. Notice we've also highlighted the enthalpy changes of formation that are here, minus 46 and minus 92 for 1 mole of NH3 and 1 mole of HCl, which is what we have in the equation. So it's quite simple, this one. We then have the ammonium chloride. Now the ammonium chloride, again, is only 1 mole, so it's nice. We're making it from the constituent elements, and we've got 1 and we've got 2. Now what we're going to do slightly different in this video is just show you the other way of getting the expression. Now this is simpler for some and more difficult for others, so just choose whichever one you want. Now normally what we'd do is we'd find the arrows that are going in the same direction. So the arrows going in the same direction here are going to be these 2 arrows here, so you'd add those together, then it equals that one. You can do it in a slightly different way and arguably a little bit quicker way. It's easiest to make the 2 arrows that are going underneath just go in the same direction. So you can add those 2 to equal the R. And I'll explain what that means in a second. But that's why we have done it both in green, because we're going to add these 2 together. Now, how do we do that? Now, hopefully you've done enthalpy changes, and you know that in enthalpy changes going in one direction, we'll have, for example, if you go in one direction, there is a positive enthalpy change. In the backward direction, it will be a negative enthalpy change of exactly the same magnitude. So for example, if we're going on this reaction here, it will be minus 46 going that way. So minus 46, but if I change it, it's going to be minus 46 times a minus, which is plus, which means it'll be 46 going that way. So all we're saying is this is a negative if we switch the direction of the arrow. And that's how you can do it. So if I switch the direction of the arrow, I can see that both arrows are going in the same direction. Both arrows are going in the same direction. I can simply add these 2 together. Now when they're added together, they create exactly the same expression as you could have done if you'd done it the other way and added the 2 other arrows going in the same direction. You get this R equals 2 minus 1, okay? Because you've got 2 and you've got minus 1 there. Okay, so that ends up in exactly the same expression. Now if we make ourselves again a little bit of space, okay, and then place that up there. Now what we're going to do now is just do the calculation. So hopefully, again, if you now understand what we're doing, get on with the calculation yourself. So we're going to start with 2 again. So I'm going to go delta 2h, and I'm going to look at what 2 is. So I'm doing 2 first just because it's the first one in the equation. So go up here, it's 1 mole of ammonium chloride. If I then look over there, ammonium chloride is minus 315. Let's do that in the pink. Okay, so minus 315. If we then go for the delta 1h, so delta 1h, and then a little bit more here, you can see that we're making 1 mole of hydrochloric acid, 1 mole of NH3. So that would be minus 46. That would be minus 46 for the NH3 if you look in the table, and then plus minus 92, and the 92 is for the HCl. If you put both of those together, that is going to be equal to minus 138. And again, all of these units are in kilojoules per mole. Okay, now that's the way we've got so far. We've got 2 and we've got 1. We just need to put them into the expression. So that basically means that we've got R is going to be equal to what 2 is. 2 is minus 315. Okay, so 2 is minus 315 and 1 is minus 138. But it's in this equation, so minus here. So minus 138. And we know a minus is in fact a plus. And so that means in the end we have got minus 177 kilojoules per mole. And that is how you calculate enthalpy change of formation, either by having the 2 arrows, adding R to another one to equal number 2, for example, or in this version where you just reverse the direction of the arrow and give it a minus to give exactly the same result. So either use the method in the previous question or the method in this question. Both of them work.